Okay, this lesson is going to be about series. And series are very simply put sequences that are added up. So the first series, we'll just write a general series as that'll be a sub 1 plus a sub 2 plus all the way up to a sub k. Okay. Now, if this were to be an infinite series, we would just let this thing go on forever. Okay? I think it's pretty clear to you that the first case I showed you, the finite series, that they will add up to a finite number given each of the terms is finite. Even if they're large, if you have 57 terms, you can eventually add them up. The question that we're really going to be investigating further is for the infinite series, which ones of those converge to be one positive number. So we're effectively adding infinitely many terms of a sequence and figuring out, well, does it get closer to a number? What is the limit? And what does it converge to? So the major question we'll be addressing is, does it converge or does it diverge? And so let me first define what convergent is. It is convergent if the limit as n approaches infinity is equal to some s, which is limit as n approaches infinity of the sum I equals 1 to n of the a sub I terms. I just changed the index of notation so that I could allow this to become infinite. And built into this is all of our formal definition of a limit. For all epsilon greater than 0, there is an n, etc. All that is built into this limit, and if that limit is some number, some real number, then the series is called convergent. Otherwise, it's called divergent. Okay, so you might think, how can we take the sum of infinitely many terms and get a finite number? The first thing I would ask you to do is add 1 plus a half plus a fourth plus an eighth, on and on. You'll see that this number never exceeds 2. Right? 1 plus a half is 1 1/2, plus a fourth, 1 3/4, plus an eighth, 1 7/8, plus a 16th, on and on and on. You'll end up with, in that case, 1 15/16, but you'll always end up with one fewer 32nd, 64th, 1/28th than you need it to be equal to. But that's why we're studying the limit, and so we just have to get sufficiently close to 2 to call it the limit. So if you add all those guys up, you'll eventually get to 2. Another example would be this one. Okay. In both of these cases, it's a geometric series, and geometric series are something that you're already exposed to. And what you learned is that as long as the common ratio, in this case 1/2, 1/2, 1/2, is the absolute value of that common ratio is lower than 1, then the geometric series converges to a number. What you learned is that it converges to the first number, 1. In this case, over 1 minus the ratio, which is a half. 1 over 1 minus a half, that's 1 over a half, that's 2. In this case, it'll be 5 over 1 minus, the ratio in this case alternates signs, so we know it's going to be negative, and it's times 2/3. And that thing will turn out to be 5 over 5/3, which is 3. So this one converges as well. And we know this just because we're familiar with geometric series. There is also proof in the Stewart book. It's not very hard to understand. I'm not going to go through it in this lesson, where you take a general geometric series. So this would be a times r to the 0 plus a times r to the first plus a times r squared. Forgot my r there, sorry. On and on and on. That this thing converges to a over 1 minus r, given that the absolute value of r is less than 1. And like I said, it's not very hard to do. Effectively what they're going to do in the book is multiply both sides by something collect-like terms, and then they'll have some expression, they'll take the limit, and this will come up as long as the absolute value of r is greater than 1. It is a good thing to look at, but it's not our primary focus since geometric series is something that you are already exposed to. Okay, so what about series that are not geometric? Let's see. Or at least first do not appear to be geometric. The one we're going to do, which I'm finding, sorry, is this one. So at first this does not appear to be geometric, but what we're going to do is just a little bit of manipulation and then it will be geometric. So n equals 1 to infinity. This is actually 2 squared to the n, that's 4 to the n. And this 3, what I'm looking for in geometric is I want to be able to write it as something times a ratio. So I need some ratio to the n minus 1. So I'm not going to write it as 3 to the 1 minus n. I'm actually going to write it as 3 to the negative n minus 1. Reason being, now I have the n minus 1, just like a general geometric series does. And then you'll see that I have 4 to the n, over 3 to the n minus 1. That's just by laws of exponents. If these were both n minus 1s, then I could have some fraction to the n minus 1. So I'm going to force this 4 to the n to become an n minus 1. And the way I'm going to do that is I'm going to multiply by a 4 right here. And now that one will be minus 1, because if you multiply 4 times 4 to the n minus 1, you're left with 4 to the n. The nice part about that is now that thing can be phrased the way that geometric series are supposed to be phrased. So 4/3 to the n minus 1. So in this case, our first term is 4, and then each successive term is times 4/3 times 4/3 times 4/3. And in this case, we do have a geometric series, a r to the n minus 1. Limits match. Problem is, common ratio exceeds 1, so this thing is divergent. So the point of this example is, remember that things that don't look geometric can sometimes be geometric anyway. And our major goal is going to be to develop a bunch of tools that we have so that when you look at a random series, that you can say, is that convergent or not? You're going to say, oh, well, I have my geometric series. Is this geometric? We'll eventually have a p-series. We'll have a harmonic series. We'll have a few different tests, comparison tests that we can go through. So hopefully that makes sense. The next thing we're going to do is actually, I mentioned the harmonic series. So we're going to take the harmonic series, which is just this series, also known as 1 over 1 plus 1 over 2 plus 1 over 3, on and on and on. And we're going to decide whether or not that thing is convergent or divergent. Well, first thing is, it's clearly not geometric. This is times a half. That's not. End of story on the geometric series. So if it's not geometric, really where can we go with this? There's actually, I'm going to project it in a minute. If it's not very visible for you, go to page 691 in the Stewart Calc book, and it'll have a good visual for you. So let me do that. I'm going to try to zoom in and see if it helps. I'm not really sure you're going to be able to see it. But it's example 7 at the bottom of page 691 again. we start with the harmonic series, which is right there. It's the one I already wrote on the board. And what we're going to do is show that we're going to find partial sums effectively. So the first partial sum, S sub 1, is 1 because the first term is equal to 1. The second partial sum will be 1 plus a half, obviously 1 and a half. The third partial sum is where it gets interesting. We're actually, instead of doing the third partial sum, we're going to skip to the fourth. So S sub 4, and the reason, you'll see why we're doing this in a second. S sub 4 is 1 plus a half plus a third plus a fourth. Well, rather than a third and a fourth, think about it as, and I'm just going to attempt, I'll leave it projected in case you can see it, but S sub 4 is equal to 1 plus a half plus a third, plus a fourth. And what we're going to do is say, well, actually that is less than 1 plus a half plus a fourth plus a fourth. Because, obviously, a fourth is less than a third. Well, 1 plus a half plus a fourth, that's 1 plus 1, which is 2. So that's S sub 4. Now, S sub 8 is going to be our next target. S sub 8, instead of doing 1 and a half and a fourth, we're going to do those, but we're also going to collect all the eighths. So we're going to take a fifth, a sixth, a seventh, and an eighth and say, well, that's actually less than an eighth and an eighth and an eighth and an eighth. 1 plus 2 plus 3 plus 4, that's 4 eighths, I shouldn't say plus. 1 plus 1 plus 1 plus 1 is 4 eighths, which is a half again. So S sub 8 will actually be less than, the S sub 8 would be greater than 1 plus 3 halves, 2 and a half. Then if you go to S sub 16, you're going to collect the 8 terms at the end and say, well, actually, these 8 terms are greater than, did I put this? Oh, I'm just realizing, I'm sorry. I put the wrong sign here. This is greater than, sorry for the mistake, greater than a half, 1 plus a half plus a fourth plus a fourth. And so now when you go to S sub 16, you're going to take terms 9, 10, 11, 12, 13, 14, 15, and 16 and say those are all going to be greater than a 16th plus a 16th plus a 16th plus a 16th plus a 16th, etc. And 8 16ths put together is another half. So S sub 16, we've now added another half. S sub 32, we will have added yet another half. But the S subs that we've given here are actually greater than these approximate numbers. So each time we're adding on more than a half, and I can give you another number. If you said, oh, I want to get to 100, the total sum to be 100, I could provide to you whatever the nth term you need to go to get to that sum of 100. Thus, this series is divergent. Okay, and this is called the harmonic series. So again, the device is, you're just going to, like if it's S sub 4, take these last 2 terms and say these last 2 terms are greater than a fourth and a fourth, and then you can say that the series that we're talking about, that we've simplified it to, diverges. Therefore, our harmonic series greater than that must diverge as well. Okay, so that's the harmonic series. The visual is pretty good in the book, like I've said a couple times, so check that out. All right, now, let me get rid of this projection and kick the light back on. Okay, there's a theorem in the book that makes a lot of sense. It's pretty simple to understand. If you know that this is convergent, then that tells you that the terms must go to 0. If the terms don't go to 0, if the terms go to 1, you're always adding an extra 1 on every time to your series. If you know it converges, then you know it goes to 0. important point here. The opposite statement here is not true. Okay? The converse. If we take the converse of this statement and we said, okay, anytime the sequence goes to 0, then the sum of that sequence, aka the series, also goes to 0. That's not true, and we just dispelled that myth via the harmonic series. So the harmonic series, if you let n go to infinity, goes to 0. The harmonic sequence, if you let n go to infinity, the sequence will go to 0. The terms of the sequence will. However, when you add them all up, we just went into detail about why it doesn't converge, it does diverge. So that's that. Now the contrapositive of this is true. If you know that the limit as n goes to infinity of a sub n is divergent, or does not, either doesn't exist or is equal to 0, not equal to 0, sorry, then the series will diverge. And I've already gone into detail about this as well. So if each of the terms converge to 2, aka non-zero, then the sum of all of them, 2 plus 2 plus 2 plus 2 plus 2, obviously is going to diverge as well. So no big surprise there. If a statement is true, then its contrapositive is true. However, its converse is not necessarily true. Let's see. Then there's a collection of rules, laws that just make sense. I'll just put one of them up here. If you have a constant times a bunch of terms, then you can pull the constant out here and then deal with the limit afterwards. These are kinds of things that make so much intuitive sense that I'm really not even going to go into great detail on. We'll do one more example and then we'll call it a lesson. And it's the sum as n equals 1 to infinity, n squared over 5n squared plus 4. Okay, so we're going to use the contrapositive rule that I just set on the board, which says if you can take the limit, let's say that this gadget is equal to a sub n, that this whole expression is equal to a sub n. So if you take the limit as n approaches infinity of a sub n, you'll get limit as n approaches infinity of n squared over 5n squared plus 4. The first thing I see when I see a series, and I'm thinking, does it converge or not, is the sequence better go to 0. So here, you can divide both terms by n squared. So you'll have 1 over 5 plus 4 over n squared. This is a technique we've already used. And you'll get 1/5. And that didn't go to 0. And if the sequence doesn't go to 0, then the series diverges. End of story there. So in this lesson, hopefully you recalled your geometric series knowledge. You understand that a harmonic series diverges, and you understand the major theorem that we just talked about having to do with sequence converging versus the series converging or diverging. And then in the next lesson, we'll get into some other tests and ways of deciding whether or not these things converge and diverge. Okay?